Today we're going to talk about basic functions and their graphs. Before we get started, let's discuss some definitions. A relation is any set of ordered pairs. So if you'll remember, an ordered pair looks something like this. It's two numbers in a set of parentheses separated by a comma. Well, in the relation, and a relation is, it could be a single ordered pair or several ordered pairs, so that's why it says a set of ordered pairs. And the domain are all of the first values of the ordered pairs, so it's all of the x values. So in this ordered pair that I wrote, the domain would be 2. The range is all of the second values of the ordered pairs, or all of the y values. And in this ordered pair that I wrote, the range would be 5. This is another example of a relation, and we are to find the domain and the range of the relation. Now, when we write the domain, we should not write the domain in parentheses, because if there were only 2 values in the domain, if we wrote it in parentheses, then it would look like an ordered pair. So the way that we write the domain and the range is we enclose it in these squiggly brackets. So we write a squiggly bracket and then we write all of the numbers in the domain. Well, we said that all of the numbers in the domain are all of the x values. So in this example, our domain would be 0, 10, 20, 30, and 36. Now for the range is going to be all of the y values. And again, we would enclose it in our squiggly brackets. And so the numbers in the range would be 9 1/10, 6 7/10, 10 7/10, 13 2/10, and 17 4/10. And that would be our range. Now, a function is a relation in which each value in the domain corresponds to exactly one value in the range. So a function can have a y value repeated as long as it doesn't have an x value repeated. So if we have a relation and the x value is repeated, then it is not a function. Determine whether each is a function or not. So if we look at A and we look at that relation, is this a function? No, it's not a function because these two x values are repeated. All right, what about B? Is B a function? Well, we have 2 y values that are repeated, but that's okay. As long as the x values are not repeated, then this is a function. Functions are usually given in the form of an equation, not just listed out as a relation like our previous examples. And in an equation, we have an independent variable and a dependent variable. There are a lot of instances in math when we use several different names for the same thing. And this is one of those examples. An independent variable is your x value. And it can be an assigned value for the domain. And the dependent variable is the y value. It depends on whatever the x value is, so that's why it's called a dependent variable. So depending on whatever you plug in for x, our independent variable, that's going to determine what our y value is. So if we look at an equation like this, in this example, in this equation, x represents the number of years worked for a company, and y represents the number of sick days earned. Because the number of sick days depends on how many years worked, it's the dependent variable. So if we were to take the number of years worked and plug it in to these spots where the x is located and solve it, that would determine how many sick days we've earned. So y depends on x. Y is our dependent variable, x is our independent variable. Now, not all equations are functions. If more than one value is y, if more than one value of y is found for x, then it's not a function. A is 2x plus y equals 6. Well, there's only one, or x is understood to be raised to the power of 1, and the same for y. So this would be a function. And that's the case with any linear equation. Any linear equation except for a vertical line. And we'll talk a little bit more about that later. But any diagonal line, any linear function that has an x and a y in it with no powers, that's going to be a function. But B, this has x to the second power and y to the second power. Well, we just said that if more than one value of y is found for x, then it's not a function. So, since y is raised to the second power, there's more than one value of y for every x. This is not a function. Now, if we had y equals x squared, if we have more than one value of x for every y, that's okay. That would be a function. But if we had x equals y squared, that would not be a function because there's more than one y for every x value. Functions are generally named with the letters F, G, and H, and we could use lowercase or capital letters. However, F is the most commonly used letter. This right here is called function notation. And the way that we read this is f of x. That's how we read that. It represents the value of the function at a particular x value. So we can take numbers and plug them in right here where the x is, and that's telling us that they want us to find what value y is at that for that x value in the function. It does not mean f times x, even though we see those parentheses around the x. That's not what it means. And f of x and y represent the same thing. So if we have an equation like y equals 2x plus 3, we can write that in function notation simply by replacing the y with f of x. And you'll see that sometimes. So basically, f of x means the same thing as y. Alright, so they want us to evaluate this function x squared minus 2x plus 7 for each of the following. And so like I said before, we saw f of x earlier. Well, if they replace that x with a number, that's just telling us that they want us to replace x in the function with whatever is in parentheses. So in this first example, they want us to replace every x in the function with negative 5. So that's what I'm going to do. All right, and it's important, especially if what you're plugging in is negative. Whenever we're replacing something in the function or we're evaluating a function, whatever we plug it in parentheses. Okay, so I've replaced all of the x's with negative 5, and now I just need to simplify. And make sure that you follow order of operations anytime you're doing something like this. Okay, so I have negative 5 squared, that would be a positive 25. And then negative 2 times negative 5, that would be a positive 10 plus 7. Okay, so if I add all of that up, 25 plus 10 is 35, plus 7 is 42. And that just means in my function, if I were to look at the graph of this function, whenever my x value is negative 5, then f of x, or my y value, is 42. So that means this point, 5, 42, would be on that graph. Okay, for the next example, for b, we're not plugging in just a single number. We're plugging in a whole expression, x plus 4. So I'm going to plug in x plus 4 every place that there's an x in the function. All right, and then remember, anytime we're squaring a binomial, we don't distribute the square. We write it twice and FOIL it. So that means that we take this x plus 4 and we write it twice, and then we're going to multiply. Okay, and then I'm going to go ahead and distribute this negative 2 into the parentheses. So that's negative 2x minus 8 plus 7. Okay, and then I want to FOIL the stuff in parentheses. So if I FOIL this, I get x squared plus 4x plus 4x plus 16. And then for this other stuff right here, I'm going to combine my like terms. I'm going to combine the negative 8 and the positive 7. So I have negative 2x minus 1. Okay, let's continue combining like terms. Okay, there's not another x squared, so I'm just going to bring it down. And then if I combine all of my terms with x's, 4x plus 4x is 8x, minus 2x would be 6x. And then the 16 minus 1 would be 15. And then that's it. We're not solving this. There's nothing to solve. We can't solve this. This part of the equation just stays like it is. They're just telling me what they wanted me to plug in. We don't work any of that side out. That's just basically the name of the function. It's telling us what we're doing with the function. So we don't move anything over to that side of the equation or anything from that side of the equation. So once we simplify everything on this right side, we're done. We can't solve it. We can't figure out what x is. So that's it. That is my solution once I've evaluated. So now we're going to do the same thing with negative x. We're going to take negative x and plug it in to the function. Every place we see an x. Okay, so I'm going to plug in negative x squared minus 2 times negative x plus 7. Okay, so if I square a negative x times negative x would become a positive x squared. Negative 2 times negative x would be plus 2x, and then bring down the plus 7. And again, once I've simplified, I can't put anything else together, I'm done. That is my solution. Linear functions are all functions whose graphs are straight lines, and a linear function would be in the form f of x is equal to mx plus b. You might remember this as y is equal to mx plus b, but like I said, y and f of x are interchangeable in functions. So this would be slope-intercept form, and this would be the equation of a line. Now, all diagonal lines, like I said, are functions. And other types of graphs may not be functions, but we can do a little test on them to tell whether they're functions or not. So if we look at these graphs, we can use what's called the vertical line test to determine whether or not the graph is a function. Well, a vertical line is just a line that goes straight up and down, and if we pass it across the graph, we can tell whether or not it's a function by how many times it touches our vertical line. If the graph touches our vertical line more than once at a time, then it's not a function. But if it only touches it in one point at a time, then it is a function. Okay, so here's my vertical line. If I pass it across this first graph, you see how it's touching my line in more than one spot at a time? So that means that that graph is not a function. But this diagonal line, it is a function because it only touches my vertical line in one point at a time, in one spot at a time. So, like I said, any diagonal line would do the same thing. So any diagonal line is a function. this graph would also be a function because it only touches my line in one spot at a time. But this one is not a function because it touches my line in more than one spot at a time. Okay, this one, even though it's pretty squiggly, it only touches my line in one spot at a time, so it is a function. All right, what about this one? Yes, it is a function. And this one? Nope, not a function. So that's how we can use the vertical line test to determine if a graph is a function. When we're looking at a graph, there are a few things that we need to remember. A closed dot indicates that the graph does not extend beyond this point and the point is included in the graph. An open dot indicates that the graph does not extend beyond this point, but the point is not included in the graph. And then arrows indicate that the graph extends indefinitely in that direction. Okay, it says use the graph of each function to identify the domain and the range. Well, if you'll remember, domain are the x values of our function. So when we're trying to determine what the domain is, we're only going to be looking at the x-axis. So if I look at this first graph, we don't care anything about this y-axis. We're only looking at how far our graph goes to the left and to the right. So if I want to see how far it goes to the left according to my x-axis, then I can see that it goes to -2. And then if I want to determine how far it goes to the right, it only goes to +1. So from -2 to +1 is my domain. Okay, and remember we put, whenever we're doing our intervals, we have to determine if that number is included or not. So let's look at those particular points. Okay, so on the graph right here where it goes to -2, on -2, I have an open circle. So that means that that number is not included. So we're going to put a parenthesis next to the -2. But then on +1, we have a closed circle. So that means that it is included. And remember, for numbers that are included, we use a bracket. So that's my interval for my domain. It goes from -2 to +1. Now we need to figure out what the range is. Well, the range are my y values. So that means we're going up and down. Now, for this time, for our y values or our range, we don't care about the x-axis. So pretend like the x-axis is not there. We want to know how far down it goes and how far up it goes. We always, whether we're talking about domain or range, we always go from the smallest numbers to the biggest numbers. So in the domain, we go from left to right. In the range, we're going to go from the bottom to the top, smaller numbers to the bigger numbers. So where does it start at the bottom? What is the lowest value that this graph has? Right here, that would be, this is for my range, that would be -1. And then how far up does it go? It goes up here to 2. Okay, so that's the top of my range. Now we need to determine what symbols we use for our interval. Down at -1, I have a closed circle. So that means I have a closed circle, so that means I'm going to use a bracket by -1. And then up at +2, I have an open circle. That means it's not included, so I use a parenthesis. All right, looking at the next graph, again, we're going to start with our domain. And the domain is left to right. Okay, so if we look at our graph going from left to right, again, we don't care about the y-axis. For the domain, we're looking at just the x's. So how far to the left does it go? It goes to -2. How far to the right does it go? It goes to +1. Okay, so now we need to close our interval. Do we use brackets or parentheses? Well, in both of these, we're going to use brackets because we have closed circles in both cases. Okay? All right, then for my range, how far down does it go? So we're going from the lowest part of the graph to the highest part of the graph. Well, what is the lowest part according to our y-axis? The lowest part of the graph would be at 0. And the highest part would be at 3. And again, both of those endpoints are closed, so that means they're included, so we're going to use brackets to enclose them. All right, let's look at this next graph. So we're going to start with the domain. We're going from left to right. Okay, so forget about the y-axis. Remember, we don't care about that. We're just going from left to right, so it goes from here to here. All right, so what is my leftmost point? It would be -2. What is my rightmost point? Be +1. Okay, so what kind of enclosures do we need to put around our numbers? For the -2 right here, we have a closed dot, so that would mean we use what? We use a bracket. Okay, and then for 1, what do we use? We use a parenthesis because we have an open dot. It's not included. Okay, now for our range, we want the lowest part of our graph and the highest part of the graph. Now, it doesn't have to be an endpoint. So if we look at this graph, the lowest point that it reaches is right here. So even though that's not an endpoint, we still are going to use that in our range because that's the lowest part of the graph. And then this is the highest part of the graph. So where does it start? Or where's the lowest part? It would be at 1, and it goes up to 5. Okay, now for 1, where it starts, and again we're looking at just the y-axis, that part of the graph is included in the graph. The only way that this number 1 would not be included would be if we had an open circle in our graph. So if our graph looked like this, it had an open circle and then it picked back up and it kept going, and it looked like that. Well, then at that point where that open circle is, where it goes through 1, then that would mean that it's not included. But since we don't have that and it's filled in, that means that that point at 1 is included in the graph, so we're going to use a bracket. And then up at 5, that one's easy because we see that we have a closed dot, so it is included, and again we use a bracket. Alright, so then for the next graph, if we start with our domain, left to right, this time, what do we see here at the end? We see an arrow, so that means it keeps going. So it continues going to the left forever. So that means it goes, if we keep going to the left, where's that headed? That would be -infinity. And if you'll remember, anytime we use infinities, we always enclose them in parentheses. We never use a bracket with infinity. And then if we go to the right, it stops at 4. And we have a closed dot, so we're going to enclose it using a bracket. Okay, now we need to go from the bottom to the top. So if we look at our graph, we're talking about our range. So the lowest point on our graph, if we're looking at the y-axis, would be 0. Again, we have a closed circle right there on the graph, and so at 0 that is included, so we use a bracket. Then we want to know how high it goes. Well, if our line leveled off right here, then we would say that the highest point was 3. But if you'll notice, this is slanted, so it's going to continue to rise. Even though it's slowly rising, it's still rising as it goes to -infinity to the left. Well, it's rising up, so on our y-axis, if we're going up, we're going to +infinity. Okay, so it's slanted, it's going to the left and up. So in our domain, the left is negative infinity. For our range going up is positive infinity. And again, we'll close that with a parenthesis. This last graph that we're looking at is called a piecewise function, or a step function, as a couple of different names. So let's look at how we would determine what the domain and the range are of this function. If we want to determine what the domain is, we're looking from left to right. We look at only the x-axis. We don't care about the y-axis. Okay, so the leftmost point that our graph covers is right here. And then the rightmost point is right here. Well, if we look at our graph, every point, even, if it's a partial point or whatever, is covered from -3 to 0, because it starts at -3 and it's covered all the way to -2, and then it stops there, but it jumps up and it goes from -2 to -1, stops there, but it jumps up and then it goes from -1 to 0. So all of that is covered in our graph for the domain. So we can say that our domain starts at -3 and it goes to 0. And then if we look at, or try to determine what types of ends we put on our interval, at -3 we have a closed dot, so we would put a bracket. And then at 0 we have an open dot, so we would use a parenthesis. Alright, but for the range it's a little different. Okay, so for the range of our graph, if we're looking at the y-axis, we start down here at -1, 2, 3, and we go up to -1. But the only problem is all this stuff in between is not covered. We're only, our range or our y values only happen at 3 points. They happen at -3, at -2, and at -1. So we can't just say that it's an interval from -3 to -1 because all of the stuff in between is not covered. So the way that we write this, our range for this function, is we just tell where it is covered. Well, it's covered at -3, and we put that in brackets because it's covered at that point. It's also covered at -2 and at -1. And then we have to join these by writing the union in between those points. One last definition that we need to cover is the zeros of a function. The zeros of a function are the x values. So again, like I said, sometimes we use different terms to mean the same thing. So earlier we talked about the domain. The domain are our x values. The independent variable are our x values. The zeros of a function are also the x values. And that's when f of x equals 0, or when y equals 0. That's the zero of the function. The y-intercept is where the graph crosses the y-axis. So the zeros are where it crosses the x-axis, and then the y-intercept is where it crosses the y-axis. So if the function has a y-intercept at 3, then it's written as f of 0 equals 3. When we have a zero of a function, or if it crosses the x-axis, my y value is going to equal 0. When we have a y-intercept and it crosses the y-axis, then my x is going to be 0. Remember, it's usually written like this. So here my x is 0, my y is 3. So my y-intercept is 3. It's crossing through y at 3, but my x is 0. Now, a function can have more than one x-intercept, but it can have at most one y-intercept. Why do you think that is? Alright, so if this were our x and y axis, if I had more than one x-intercept. Say if I had something that looked like this. Would that pass the vertical line test? Yeah. So, and it crossed the x-axis in more than one point. But if I had something that looked like this, would that pass the vertical line test? No. So, and that has more than one y-intercept. So a function can have more than one x-intercept, but it can only have one y-intercept in order for it to be a function.